Um, would you please confirm me that you're seeing the PowerPoint, people? Can you confirm me that you are seeing my PowerPoint?
Yes, doctor.
Okay, thank you. So we have to do that for every element. Okay, I'm going to check, for example, for the bar 3. Okay, let me go back to recall in element 3. Element 3 goes from 3 to 4. Okay, element 3 goes from 3 to 4. Okay, so what we have to do now, let me change color just to color, let's use, how about that? How about that, Barcelona? How about that, Barcelona? Okay, so let's analyze element 3. Where are you? Oh, here it is. Okay, so, oh, Jesus, where are you? Who is the point? So this part here, these two equations are the forces at joint 3 to equilibrate the element 3. And these two are the forces in the fourth joint required to equilibrate element 3. Now, again, this vertically is multiplied by element 3. And this other part is multiplied by joint 4. Okay? So in this way, we can split, we can recognize in every element stiffness matrix, the contributions for the equilibrium of each one of the elements. And that's expressed as function of the displacement of the joints. Now, this is each one of the stiffness matrix of the elements. What we have to do now is put them together. Okay, this is something I just said, okay, that we can recognize here that we have it's in every matrix we have we can split like this, like this. And we can see that in every element, in every joint, we have 2 degrees of freedom. So every joint can move in the X and in the Y direction. Okay? Now, let's put them together. To do that, we have recognized that there is one single way of calling all the displacements. So this is joint 1, joint 2, joint 2, joint 3, joint 3, joint 4, etc. And then the numbering, it's common for every element. And the second part is that we have to have consistency with external forces. So in this point, of course, there's only one element. So all the external force here will be applied for the equilibrium of the element 1. But in the second joint, see, this is the second joint, we have to be careful because, as we said before, if we have an external force here, part of that will be employed for the equilibrium of the first, of the second, and for the fourth element. That's what we're saying here. Part for the equilibrium of the first, second, and fourth. And we have to be careful because we have to do that for the X and for the Y directions. Okay? So in this way, we put all of these four matrix in one single big matrix. Oh, shoot. Damn it. I don't know what happened. Let me go back again. Jesus. Okay. Now, this is the stiffness matrix of the first element. We recognize four parts. This is the stiffness matrix of the fourth element. Okay, and we recognize again four parts. Okay, and this is the global stiffness matrix. Right now, it's full of zeros. This is something that you have to do. Why? Because what we do is we add these values to the corresponding position in the global. Now, if you start with values different than zero, if you add, then the result, it includes some error. Okay, so what we have to do before adding is to fill this with zeros. And then we recognize this element one connects joint one and two. So this is the first force of the first joint, and this is the first joint. Vertically, this is the first joint. Here you have the first joint. So these four elements go here. This got here. So that's for the first joint, forces of the first joint. Similarly for the forces of the second joint, like that. So you add these values to what you have here. Now, this relates element two. Element two goes from 2 to 3, right? From here to here. So this is the first part, the first rows expresses the required external force for the equilibrium of the second joint. And this is for the fourth, I'm sorry, I'm talking about the fourth element. So because this is multiplied by the fourth, the displacement of the fourth joint. Now, for the forces of the fourth joint here and there. So what we do is we take these values and add to the values that we had before in the global stiffness matrix. So that's the result. So in here, you see that you have all the contributions from the four elements. And you see here, for example, that this space here is full of zeros. That means that this is the external force in the first joint related to the displacement of the third element, of the third joint. But you see that this and that are not connected by any element. So that's why we have zero here. Okay, and this is what we are doing. That's what we call consistency. What else? Okay, remember, this stiffness matrix is the global stiffness matrix. Right now, for example, I have 4 joints, and this is 8 by 8. Okay, because every joint has 2 degrees of freedom. Okay, now, if you calculate the determinant of this, there is a question from somebody?
Yes, doctor, I have a question.
Yeah, go on.
So, so for these kind of problems, every time we are going to consider the boundary conditions in the global system, in the global matrix, right?
Yeah, yeah.
That's why, okay, that's why we have the zeros in
Yeah.
one, and okay.
No. These zeros are because these zeros, remember, the first 2 rows express the external force in the first joint. And what we're saying is that this force do not depend on the displacement of the third joint. And you see here, if this moves, that doesn't affect the reactions here because they are not connected. That's what we mean by this. Okay, see, I write these letters here to help me recognize the different columns. Similarly for this thing here, this just to remind me that these two are for the first joint, second, etc. And this is just because they are not connected. That's all. Similarly here, for example, this is the, remember, these two rows express the equilibrium, I'm sorry, the external forces for the equilibrium of the fourth joint. That's this one here. And we are saying is that they are unrelated to the displacements of the first joint. And you see that joint 1 and joint 4 are not connected. Okay, that's why these elements are 0. Not because this is 0, no, it's just because this and that are not connected. That's the reason. Better?
Yes, doctor, thank you.
Okay, no problem. Okay, now let's go on. Now, remember, if you calculate the determinant of that matrix, that's going to be 0. So what we have to do is we have to to apply boundary conditions and then solve first for the displacements, unknown displacements. Okay, so right now, we recognize that joint 1 and joint 3 are simply supported. So joint 1 cannot move neither in the X or in the Y direction. Similarly for the third joint. So here, this point here cannot move in that or in that direction. This point here doesn't move in that or in that direction. That's what we have to solve. Now, what else? Here, in joint 2, the external force is 0. So here, that's what we're saying here, that the external forces are 0. I'm sorry, this one here. And also here, you see that in the X direction, there is no force. In the Y direction, this is the force, but it has to be negative. That's what we are saying here. So this is boundary condition. This is natural boundary condition. Okay. Now, right here, you see that these values for the displacement have to be 0. Okay. And what we're going to do is simply here, we're going to receive the reactions. Okay, so what we should do is we should take a subsystem. So we take some of these equations and put it down here, and we will have 4 equations and 4 unknowns. Okay, but the problem is that in this case, you should try and take the system would be something like this part here. Damn it. So we would take this, not this, and that. Then we will have this and this. Okay, this is going to be our system of equation. So the first row would be this one, this element, 1, 2, 3, and 4, 1, 2, 3, and 4, etc. But that's very complex, okay? So instead of that, this is what we are going to do, okay? In the last version of this file, I gave you this, okay, in page 20. Okay, let's suppose that we have something like this, okay? And when you see this large D or large F, that means that you know these values, okay? These are known values. Okay, now let's suppose that we do not know D1, 3, 4, and we do not know the force F2. Okay, so what we have to do is, this is what we have done, the first subsystem. Okay, so we say, okay, this is multiplied by this column, right? Because D2 is known, okay? And we take this, this and that equations. So we do all of that, and this is the first subsystem. Okay, so we cross this, and we take the rest of the values here. And in general, D2 is something that we know that, so we multiply by this, and right now we have to move it to the right because it's a known term, it's an independent term. That's what we see here. The second, I'm sorry, the second term will be this times that, and since we know D2, we move it to the right, and this is what we have here. And same for the last one. Okay, so this is the first subsystem. In general, so far, D2, we have taken a 0, but D2 could be something different than 0. That's why we put it like this. Okay, and then what? We can solve it. And this is an example. Okay, let's suppose I have this. This is an example. Okay, so this is a 4x4, and let's suppose that I have F1, F3, and F4. And let's suppose that D2 is minus 0.2. This is a known value. So what we have to do is we take this subsystem. This is what we have here. So we cross this times that, and the rest is here. And now we multiply minus 0.2 times 2, that's minus 0.4, and move it to the right. So it's going to be 1 plus 0.4, that's this. Minus 0.2 times 5, that's 1, minus 1, move it to the right, so that's 4. Minus 0.2 times 3, that's minus 0.6, move it to the right, plus this, that's 4.6. So this is the system of equations that we see here. We solve it like this. What I'm saying is that this step from here to here is very complex, very, very complex. So instead of that, this is what we tend to do. It's the same process, the same equations, but instead of extracting the first subsystem, what we do is we replace this value, okay, in the main diagonal, okay, we replace by a large value, like I'm calling a big value, okay? Big value, okay? Now, let's leave the 4 displacements as if they were unknown. And here, I have this the same big value times D2. D2 is the value that we know. Okay, let's think for a minute on this equation. Since this is a very big value, okay, when you multiply this 4 by this 4, the most important term is going to be this big, because this is very large. So it's going to be big times D2. And on the right-hand side is approximation. We say that this is equal to big times D2. So the solution of this equation, since this is big, is going to be that D2, this is the unknown, is going to be D2. So we recuperate what we have to do. And the rest is just solved by itself. I'm sorry, I made a mistake here because I copied the equation. This term should be here. Would you please correct this in your notes? I'll try to correct it and post it again, but please, so far, correct it. Okay? So how big is big? Well, it's something that you have to do. For example, in this case, I have the same example. Okay? We know this D2. So instead of this 5, what I do is I replace this by a big value. For example, e to the 12th. That's large enough, okay? On the right-hand side, okay, what we do is we replace the big value, this 1 to the 12th, and multiply by a known value of V2. In this case, the known value is here. So the result is 0.2 minus 0.2 times that is going to be minus 2 e to the 11th. And the other values is 1, 3, 4 here, F1, F3, and F4. You can solve it. I did it with Excel, and this is the solution. Of course, this equation produces minus 0.2, as we explained here. Okay, and the rest, you see, this is 3, it should be 3 exact. I have a small error here. This should be 5.8, and it's 5.79999. And again, for the last one, it's basically minus 19. People, is there any questions about this? Any questions about this, people? Okay. I can tell you by experience, okay? In going from this system of equation, of this matrix, coefficient matrix, to this one here, when you have, in this case, I have only one unknown, and I'm sorry, known displacement, but it's a mess. Believe me, I did it in 84, and it was, I had to use, remember, 3 sub-indices in three branches. It was a mess. And then after some time, I knew about this algorithm, and it works. Okay, so how big is big? For example, the value that I usually do is 1 to the 20th. The problem is that when we do these operations in Excel, okay, remember after you do this, okay, does anybody remember the procedure in order to solve system of equations? Does anybody remember the algorithm for that? No? Come on. Anybody?
The inverse matrix times
No. You can inverse that, but the problem is that inversion is very expensive. See, if you take, for example, 10 by 10 matrices, that's okay. But I'll give you, I remember in engineer Jungan, that was probably in 2011, we had 300,000 equations. And to get the inversion of that, it was, so what we do is we apply, come on, I think it was Gauss, people correct me, reduction and back substitution. This is what we used, okay? So after we have this, we apply this method and we go. In the case of Excel, he uses inversion because there is no for this. And that produces a very large problems because he works with minors and things like that. So you have to be careful with this value. But when we apply this type of processes, a value of 1 to the 20, that's my favorite value. And that works correctly. So if you have any doubt, what you can do is you try, for example, 1 to the 20th, and then repeat it and try it with a different value and compare the difference. Now, remember that we have to check is that this is the displacement vector. We call it like this. Remember, this is in the global reference system. So what we have to do is take this and multiply by the original. And then you are supposed to get 1, 3, and 4, and see if you got it. And that's what you have. So that means that the system is correct. Okay. Now, is there any questions about this process, people? Otherwise, I'm going to go back and apply this.
I have two questions.
Yeah, go on, please. No, name first, because I want to recognize the voices at least.
I'm Ordóñez.
Okay, go on.
The first is.
Could you please turn on your camera, because I don't want to talk to the wall. Okay, go on.
Okay.
If you can.
Yes. In the values of 1, 3, and 4 is only the number or displacement, right? The 2, the 1, the 3, the 4. This is
in this example, this is
yeah.
like you had, for example, forces. This is like your big K. But in this example, D2 is known. So this is F1, F3, and F4. In this case, D2 is minus 0.2. This is the example that we're solving. Okay, and this is the displacement. This is also displacement. So this is D1, this is D3, and this is D4. So what we do is, this is what we do so far up to now. But the problem is that I insist that in going from here to here, it's a mess. So instead of that, what you do is something like this. This is wrong, wrong, and wrong. So what you do is you replace in the main diagonal, okay, in the main diagonal, this value, which is going to be multiplied by this D2, which we know, this is known value. We replace it by the big value. And on the right-hand side, okay, you take this value and replace it by the same big value and multiply by the value of D2 that you know. Okay? Now, since this is very big, so from all of these 4 terms, this is the most important. So it's like saying that this is so small that we can neglect them. And the result is going to be that D2 is going to be equal to the correct value. And what we save is that this process, it's an extremely messy process. So this is what people do. Okay, Mr. Who was asking me?
Ordóñez.
Ordóñez, okay.
About for example, that's procedure about the lesson, for example, the quiz. This is a procedure that we should follow.
I haven't thought about the lesson, the quiz. So I cannot tell you anything about that because I haven't thought about it. Have you thought about it?
No, but my question is because
the thing is this: don't try to become an expert in quizzes. Try to become an expert in finite elements. Okay, Mr. Ordóñez?
Yes, my concern is because in the assignment I had a matrix for 4 times 4 matrix, right? So I should use the Excel table. So in the lesson we don't have an Excel table.
No, in the quizzes you have no Excel.
Yes, that is my concern.
No. See, that's a problem for me. I have to solve that, and you have to trust me. I am concerned that the time for the quiz is limited, and I have to give you something that I consider that is adequate for the time that you have available. Yes, I'm not going to give you a 5x5 system of equations, but I can give you something And the thing is that, as I said before, I don't want to overload you with a system of equations that you cannot solve in see, to do it, some of these processes, you need a very long time. So I need to give you something that you can do in a decent amount of time. Don't worry, that's my job. What you have to show me is that you understand the process, the finite element process.
Yes. Thank you.
Okay? Okay, people, now let's go back now to our problem. Here. So you see that we know d1x, d1y, d3x, d3y. What we do is we replace them by a big value. And on the right-hand side, we replace it by, in this case, k11 times the value that we want. In this case, the value is 0. So k11 times 0, that's 0. Same for this one here, that's k22 times d1y. That's k what? 55 times 0, and k16 by 0. And then we proceed for the solution. Since this is a very large value, all of these are very small, so it's basically this times d1, and it has to be equal to 0. So the solution is basically that 0. So I'm writing here up to the 6th decimal. And up to the 6th decimal, d1x is 0. So that's very close. So in this case, we got d2, d3 again is 0, and d4 is like that. So if you can take this part, this, and that, and prepare a subsystem, and then solve it. But it's much easier if you do it like this. Now, what's the next step? The next step, remember, is to get the reactions. Okay? So right now, these values we know, d1, d3, d3. And we have calculated d2 and d4. So right now here, we know all of these, all the displacement in the global reference system. One more time, let me put it here. This is displacements in global reference system. So for example, here, this joint moves to the right. So, and moves to the right 0.00143. Moves, I'm sorry, moves downward. Moves downward. How much? Minus 0.00027, right? But the problem is this is a bar. So the only reaction that this bar has is in this direction. Okay, so when you apply a force in this direction, the bar reacts. But here I have a displacement to the right and downwards. So what we have to do is take these values and calculate how much this point, this joint, has moved in this direction. So if you find that this value, that this point moves to the right, this element will be in tension. If you find that this value moves in this direction, this element will be in compression. But we have to calculate from this and from that, we have to calculate how much it moves in this direction. That's the local direction. Remember, these are global. We have to go one by one and calculate from the global back to the local. And with the local, we can go on and calculate the strains, stresses, and internal forces. Let's take a break.